Hey everyone, and welcome back to The Explainer. Today, we're diving into something we all pretty much take for granted every single day, but that literally shapes every single aspect of our planet. Yep, we're talking about water. We're going to go on this incredible macro to micro journey to really understand the forms, the occurrences, and the wild properties of water on Earth. We'll start way zoomed out, looking at its massive distribution across the atmosphere, the surface, and underground, and then we're going to zoom all the way in to explore its incredibly unique physical and chemical quirks.
Here is our quick roadmap for today's explainer. First, global water distribution. Second, the hydrological cycle. Third, surface water and wetlands. Fourth, hidden reserves, groundwater. And finally, Section 5, the unique properties of water.
All right, let's jump straight into Part 1, global water distribution. Basically, where exactly is all of Earth's water hiding? Okay, let's dive right into this because the sheer scale of these numbers is absolutely staggering. Our oceans and seas hold a massive 94% of the Earth's water volume. To put that into perspective, if you took all that ocean water and spread it evenly across the entire globe, you'd be standing under a layer of water 2,500 meters deep. But here is the absolute critical takeaway for us. Our lakes, our reservoirs, and soil moisture, they hold less than 0.01% of the total volume. It's crazy, right? We live on this giant blue ocean-dominated planet, but only a tiny fraction of that is actually usable surface fresh water.
Which brings us nicely to Part 2, the hydrological cycle. Let's look at how all this water actually moves around.
You see, having massive volumes of water just sitting in the ocean is one thing, but how it shifts states and moves around is what actually sustains life on dry land. Let's just follow a single water droplet on its journey, right? It falls from the sky as precipitation, think rain or snow. From there, it can soak deep down into the earth, which we call infiltration, or it can flow directly over the land as runoff, feeding our streams. Eventually, heat gets involved, causing evaporation from surfaces back up into the atmosphere. Oh, and we absolutely cannot forget transpiration, which is essentially water vapor breathed out naturally by plants.
So combining a couple of those ideas gives us a super important scientific term: evapotranspiration. This is the combined tag-team process of evaporation from water bodies and transpiration from vegetation. Now, why should you care about this long word? Well, because this specific movement through soil and plant life accounts for a massive 62% of our globally renewable freshwater every year. It is literally the engine driving the global water cycle.
Now, you might be wondering, how do scientists actually track this stuff if it's mostly invisible vapor? Well, they have some pretty brilliant techniques. The IAEA has run these amazing real-world case studies over in India and Southeast Asia using isotopes. By mapping the specific isotopic makeup of rainfall, so tracing tiny elements like tritium, oxygen-18, and deuterium, scientists can perfectly trace how water moves through a local ecosystem. It's basically like putting a microscopic GPS tracker on a raindrop. No way, right? It's incredibly precise.
And all of this next-level data collection has actually helped spark an entirely new discipline called eco-hydrology. This field is all about stressing the shared pathways between water systems and ecosystems. Instead of looking at hydrology and biology as, completely separate things and isolated boxes, eco-hydrology looks at the whole shebang. It takes the flux of all waters into consideration to build much better, holistic models of our environment.
To make these complex models a bit easier for policymakers and city planners to digest, scientists use a really handy shorthand. They split it into two concepts: blue water versus green water. Blue water is probably what you picture when you think of water. It's the stuff flowing in rivers, lakes, and aquifers. But green water? That's the invisible water locked up in soil moisture. It supplies our forests, our grasslands, and our rain-fed crops. Green water is what ultimately evaporates right out of the plants. Moving on to Part 3. Surface water and wetlands, the visible, dynamic waters we interact with most.
Now, even though these surface waters hold a measly 0.3% of the Earth's total fresh water, they somehow represent about 80% of the renewable water we humans rely on every single day. Because they're so dynamic, these rivers and lakes provide a vast array of services to us. They counteract crazy seasonal floods and droughts through large reservoirs, they give us global shipping routes, vital irrigation for our food, spots for recreation, our main drinking water, and hey, they even generate our hydropower.
But here's where things get a bit complicated, and it really shows how our scientific understanding has to constantly evolve. You've probably heard the generalization that wetlands act like giant natural sponges for flood control, right?
Well, a massive 2003 review by Bullock and Ackerman found only, quote, limited support for that idea. They explicitly warned against making simplified statements about what wetlands do. Why? Because surprisingly, some wetlands actually make floods worse, or they block water from recharging underground aquifers. It turns out a wetland's job depends entirely on the specific local landscape it's sitting in.
Which brings us to part 4, hidden reserves, the crucial groundwater locked up beneath our feet.
Get ready for this one. 96%. Yeah, 96% of Earth's unfrozen fresh water is completely out of sight, stored deep underground in aquifers. Half of the world's megacities rely on it to survive. It feeds our natural springs, it keeps surface wetlands alive, and globally, it provides up to 40% of our drinking water. It really is the silent, heavy-lifting giant of the entire hydrological cycle.
And finally, part 5, the unique properties of water. Let's look at the molecular magic making this all happen.
This is the big aha moment of today's explainer. We are zooming all the way in from the massive planetary scale down to the tiny microscopic molecular level to see why water behaves the way it does. And to get us thinking about the complex chemistry of H2O, I want to ask you a super basic question. Why does ice float? Seriously, have you ever paused to think about that? Almost every other substance in the known universe gets denser and sinks when it freezes into a solid. So what's water's excuse?
Well, the answer lies in water's completely bizarre density curve. As water cools down, it actually reaches its maximum density at exactly 3.98 degrees Celsius. But then, as it gets even colder, dropping below 4 degrees, it actually expands. It becomes less dense. By the time it locks into solid hexagonal ice, it's about 9% lighter than the liquid water around it. And why does this matter? Well, if water didn't have this weird quirk, our lakes and oceans would freeze solid from the bottom up. Every winter, all aquatic life would literally be wiped out. Instead, that floating ice forms a perfect insulating blanket for the deeper water below. Nature's pretty amazing, right?
Okay, here's another core question to get us into water's unique chemical behavior. Why do we call water the universal solvent? How does it have the power to dissolve everything from the salt on your table to the vital nutrients pumping through your bloodstream right now?
The secret is completely in its shape and a funky concept called polarity. You see, a water molecule isn't just a straight, boring line. It has a bent, V-like shape. Because the big oxygen atom hogs the electrons tighter than the two little hydrogen atoms, it creates an unequal sharing situation. So you end up with a molecule that has a slightly negative charge on one end and a slightly positive charge on the other. Because of this polarity, water basically acts like a tiny, aggressive magnet. It literally tears apart and dissolves salts by attracting and ripping their ions apart in the water.
And honestly, it is exactly these microscopic quirks that make the massive global water cycle possible. Water has a super high specific heat capacity, meaning it takes a ton of energy to heat it up. That's exactly what buffers our global climate and stops wild temperature swings. It also has high surface tension, which is what allows those little insects to literally walk across pond water. And then there's capillary action. Thanks to water molecules wanting to stick together and stick to other things, massive trees can pull water straight up from their roots to leaves over 100 meters in the air, totally defying gravity.
So from the mind-blowing 94% volume of our oceans, all the way down to the tiny bent polarity of a single H2O molecule, everything in hydrology is perfectly, intimately connected, which leaves us with this final thought to chew on. As our global climates inevitably shift and our hidden, vital groundwater reserves are tapped faster than ever, how will our evolving understanding of water's micro properties and macro movements ultimately dictate the survival of our ecosystems? Thank you so much for exploring the amazing fundamentals of hydrology with me today on The Explainer. Keep learning, keep asking questions, and I'll see you next time.